part of the reason why I didn't, because they get really long. But if they're causing confusion, then we should just go ahead and make it long, right? So this is the first measurement that you make when you put a blank filter pad into the spectrophotometer and you make a measurement. That's your reference measurement. In our spectrophotometer, you can have it store that scan, and it will automatically subtract it from all of your sample measurements, which is helpful because then what you look at on the screen is your sample and not your sample plus the instrument noise and the filter pad and all of that. So first you make this measurement, then you put your sample filter in there and you scan again. That's the sample on pad scan, right? This can happen automatically in your spectrophotometer, or you can save them independently and do the math yourself. Okay. I've called this sample baseline correction, B correction. Does that sound good? Okay. Then we apply the path length amplification factor to this to correct for the optical path being different from the geometric path. So the baseline corrected sample absorbance raised to 1.0867 multiplied by 0.323. Yes? One would think that it would, but those are actually second order sources of variability. This correction was run with a variety of different species of different cell types. However, in order to do this correction, you have to be able to run a sample in a 1 centimeter cell, which means it has to be pretty concentrated. And so cultures make the best source. Darius concentrated some natural samples and then put those in a 1 centimeter cuvette to do this correction factor. And there's some variability, but it all lies along this pretty nice equation. I've done it for a number of different cultures just to verify that it looks the same, and it does. It's an empirical model.
And I mean, for me, there's just too many significant digits. When I see this
I know.
before, after,
I know. You are so, we actually have done an uncertainty budget on this. Yeah. Honestly, but it makes people feel better to have numbers. But I will say this, and I said this to a couple of people. Before I had a center-mounted integrating sphere, I did transmission mode, which I'll spend a few minutes on because I had a question after class. And so because I am just not an empirical. I'm not good with empirical models because of exactly those things. They work for the situation at hand. So I looked at the light field of the filter, and I said, what would happen if we assumed that it was diffuse, a diffuse light field with sort of randomly oriented angles of light? And we'll talk about radiometry next week. But essentially, you can model what the average angle looks like in a diffuse light field. And it turns out the average angle in a plane is 60 degrees. And the cosine of 60 degrees is 0.5, which says that your path length through that diffuse light field is overestimated by a factor of 2. And so I would say that the path length amplification is 2 times too big compared to the geometric path length. And so when Darius and I compared his model for transmission mode and my model for transmission mode, they were indistinguishable within the uncertainty. So one was derived from a theory with the assumption of a diffuse light field created by multiple scattering in the particles, and one was derived by empiricism. That is, in one sense, a piece of closure, right? But the problem with the transmission mode is that, and I'll show you, is that it has other sources of error that you have to account for. And so if you have the opportunity to use this, I recommend this. And as you go forth and graduate and set up your own labs, and if this is going to be the work that you're doing, invest in the center-mounted integrating sphere. Your life will be so much simpler and so much more accurate. So we are at correction for the path length amplification. And then we compute the absorption coefficient. So now we have the absorbance by the sample that has been baseline corrected and amplification corrected. How's that? I tried to do it as short as I could. And that's what goes in here to be corrected for the geometric path length. Dimensional change, or unit change, and conversion from log base 10 to natural log. Yeah? Okay. So, there's a quick question about the center-mounted versus transmission mode. So I've showed you this. The other mode, if you don't have an integrating sphere, and it's actually the mode that we're going to use today for CDOM, because CDOM doesn't have particles or scattering, is where you have your light source coming in, your sample is here, and you have a detector on this side. And so you're literally just measuring transmission through the filter. And so when the light comes out of the filter, it's coming out at all different angles. So we put a diffuser so we can collect all that light and send it to the detector. But we also have some scattering out the front. Not as much because most of it gets absorbed, but we are losing some of this. And part of that is corrected with the baseline, but not all of it. And the way that we know is because, can I erase this? Don't we have this? I just need more space. Or I can just move it here. The way that we know is because if we measure the absorbance in an integrating sphere of, say, a culture, I'm measuring out to here. It looks like this. If we measure it in transmission mode, we get this. And phytoplankton don't have absorption out in the infrared. And in the integrating sphere, because we collect all the scattered light, we can validate that. But in transmission mode, we have this signal here, which is scattering, but it's methodological. And so in transmission mode, if this was the instrument that you had, what would you do? If you know that your instrument does not detect scattered light, and you know that that is causing an overestimation of absorption, and you know that phytoplankton don't have an absorption signal in the near infrared, how would you correct this? Just subtract it. That is called the null correction. You figure out what this value is, and you subtract from the whole spectrum.
And that's constant for the whole spectrum? Like,
Well, I don't know. What do you think?
probably.
To first order, because the filters are white and scatter pretty much equally in all directions, it's not a bad assumption for phytoplankton on filter pads in transmission mode. It's not perfect. The problem is, what happens if you don't have phytoplankton? What happens if you have non-algal particles? So here's what the absorbance by non-algal particles looks like. in a center-mounted integrating sphere, they actually do have some absorption. And so if I measured this in transmission mode, how much do I subtract? Because I don't have the white curve. I don't know how much to subtract. And so the full thing gets subtracted in the null correction. And you end up underestimating absorption. And then the real problem is, in actuality, you probably have both. And you just don't know how much. And this can be quite large, the null correction. And so you're subtracting something that you don't really know what it is. Yes?
Many people also subtract when they measure CDOM.
Yes, they do. So if this were a CDOM, because they measured in transmission, it's usually pretty small. Absorbance by CDOM. And they subtract that. So the question is, Emmanuel's making faces at me. Yeah?
Is there like anything else you do with the filter, like you're extracting to get rid of the liquid?
We're almost there. I realized that I didn't finish that. I thought I was done with filters, but I'm not. Almost there. I'm leaving this as a question. We have everything within our capability to do this. Because we could get a high CDOM sample that we could measure in an integrating sphere in a cuvette. And we'll take a look. See how good the filter is. There are still so many questions to work on.
Is it the filter? Is it due to the filter? Is it due to...
Put a whole sample in. But then you've got particles. Like, I don't know. This is the problem. Like, everything that you do.
People do it. I just reviewed a paper where somebody did it. And when I asked why, they say standard procedure
Standard procedure.
to blind the CDOM.
Yes, standard procedure is the anathema of this class. You don't do things because that's just the way we've always done it. And I am just like taken back to my PhD defense, where one of the members on my committee, Norm McCormick, who is he's a nuclear physicist, but he did radiation, atmospheric radiation. I measured things in transmission mode and I subtracted the null. And he said, "Why'd you do that?" And I said, "Well, that's what we do in optical oceanography." And he's like, "Why did you do it?" And we had this huge debate in my defense. So, still the same problems. 100 years later, we're still working on the null correction. But I will tell you that after doing a bunch of these types of measurements, I don't subtract because I would rather just say that that's my uncertainty because of the filter pads.
Use that as your error bar?
Yeah. Or just, I cannot resolve my absorption within this much. Right? Or if you subtract it, say, I subtracted this much. And it's somewhere in there. It's somewhere a little bit less than that, right? Just be honest. The problem is nobody used to put error bars on anything. And so now as soon as you put an error bar on it, it's like, oh my gosh, there's error bars. It looks terrible. Right? And you have to be bold. You have to wear your error bars proudly. I'm going to show you some error bars in a second. Oh, wow, and here we are. The uncertainty calculation. So I run 3 blank pads relative to a baseline blank pad, just because every filter is different. And sometimes you get the bad one on your baseline, right? And you don't want to use that one. And then I compute a standard deviation spectrum from those blank measurements. And you hope that it's flat, and you hope that it is near 0, right? That's what you want. It's not. It won't be. And then I take that standard deviation spectrum, which should look something like, this is what I want. This is what I often get. there's always junk going on in the blue because it's hard to keep organic matter out of anything. And so then I compute the absorption. I put it right through the whole equation. I do path length amplification. I do the whole thing. And you note that it's going to be different applied to every sample because the volume that you filter for your sample is different, right? I'm going to filter 100 mils for this sample and 200 mils for this sample, but I have to calculate an uncertainty from this blank pad signature. Yes?
When you say you substituted for A in the absorption equation, do you literally just put it in the equation and just
Yes.
the absorption, or did you do actual error propagation?
So this is a sample variability calculation, which is different than an error propagation. Yes, we're getting to that too. Okay, good question. So the absorbance is different for every sample, and so we've got this signal to noise. How big is your blank pad variability relative to your signal? And so, you know, you just put it right in there. This is where you put it in. Just do the calculation. And then for sample A, you'll put in the filter volume for sample A. All right. So here's what it looks like. This is the derived particulate absorption for 2 different samples. I filtered the same volume. So this might be the sample you would collect off the dock. And this might be a sample that you collected in the Sargasso Sea. And magically, they have exactly the same composition of phytoplankton because I modeled it. But imagine that I only filtered 100 mils. If I filter 100 mils of a really thick sample, I'm going to have a really high absorbance reading in the spectrophotometer, right? If I filter 100 mils of a really dilute sample, I'm going to have a really low absorbance, right? There's just not going to be much on the particles, so it's going to be noisy. And so when you put the so in that case, my absorbance for the Sargasso Sea might look like that, and my absorbance or optical density might look like that, right? So the signal to noise is very low here. The signal to noise here is very high. And so you don't want to be publishing these error bars. So how would you solve this problem? Just filter more water, right? Just do it. It's a pain in the neck. Just filter more water. Okay. So, yeah. All right. So this is what happens when I do that. So now I have filtered enough water on that sample so that now my signal looks more like this. I did a large volume. And so now my uncertainties are small. But because I correct for the volume, I still have a low absorption value, right? It's a factor of 10 lower absorption because it is. It's the Sargasso Sea. But I have very small error bars. So the key is, going through all of that, filter more water. You need a high optical density of your sample. I'm sorry, this says optical density should be absorbance relative to your blanks. This is why you want it to be between about 0.1 and 0.4. Just filter till you get there. And if you haven't done it before, you'll just have to practice, and you'll see the color on the pad, and you'll be like, yeah, it's about right. Right? Sort of like, I don't know, a lot of analogies. Anyway. Okay. Partitioning. Who asked for partitioning? Extraction. Someone just asked me about extraction. You asked. Your first scan. No, you asked. You asked. Your first scan is the particulate matter, right? Then you put it back in the filter cup. You put methanol on top, because methanol is very gentle, not gentle enough to drink, but gentle to extract. And then you scan it again. So you filter that through. It removes all of the pigments. So particulate, there's your scan of non-algal particles, and then you subtract them, and you get the phytoplankton curve. Total particles, non-algal particles, and phytoplankton. Is that? Yeah. So we'll do that in lab. Just remember that the phytoplankton parts, the cellular material that doesn't have pigments, shows up here, which is fine. Detrital pigments, like phaophytin and phaeophorbide, where do they show up?
Extracted.
They get extracted. So which component do they show up in? Phytoplankton. So your phytoplankton are the in vivo pigments, but it could be the dead pigments that are in fecal pellets. But they get extracted, so they're going to show up here. The fecal pellet will show up here, but the pigment's in the fecal pellet. So if you have a lot of dead phytoplankton around, the spectrum that you derive will look very detrital. You'll see the peaks shifted to look more like detrital pigments. What did I say about phycobilly pigments yesterday? Cyanobacteria pigments? Not extractable, right? So what you end up seeing in that case so if this is your first scan, and then you extract, well, actually, we can make it a little bit more. They look kind of like that. And then here's your non-algal particle scan. You just know that you've got other pigments in there, right? So you can extract again with a phosphate buffer, or gently extract with boiling water, and you'll get your non-algal particle that looks more like that. And then that's the one that you want to subtract from this to get phytoplankton. Okay. And we already had the question about inorganics and organics and combusting. Okay. Good. Filter your sample. You want a high loading, but not muddy. Right? You don't want it to be muddy. You want a reference blank filter. Extract to separate the particulates and non-algal particle. In your computation, you have the geometric path, you have the optical path, you calculate absorption for both particulates and non-algal particles, and you get it all the way to the absorption coefficient, and then you subtract the coefficients. Do not subtract the absorbance. Okay, that's that. Get you the wrong answer.
Do you do the same amplification correction for both NAP and phytoplankton?
Yeah, it doesn't look like it's very different. When you put them together, they show up on the same suite of points, which says that it's more about the filter and less about what's on the filter. Okay. Manuel, you want to do this? You're going to do it again in lab. How many people have worked with these? Do you love them? I do. I love these. I will be in lab with you in my spirit, but okay. It gives you a quantitative measurement of absorption and attenuation. And it actually gives the data out as an absorption coefficient per meter. Not absorptance, not absorbance, not optical density, not any of that. It gives it to you. We calibrate it with pure water, right? So pure water becomes our reference. And the corrections that you're going to have to think about are temperature and salinity, because remember we talked about how the absorption of pure water varies with temperature and salinity. We're actually going to do some experiments on that. And it's not the perfect configuration for absorption and attenuation based upon the thin layer model, or the thin layer theory that we derived earlier. So we'll talk about some strategies to get the best measurements out of these. I still have the first one I ever bought when I was a postdoc, and it still works, and I use it all the time. So it's 100 years old, and it is the AC9, and it is so robust. I'm not kidding.
You're so much younger than
I know.
You say you were born in, what was it, 87?
That's right, I was.
I'm
Seneca Caucus age. Sorry, is that like dog years? No, but seriously, it's like 30-something years old. And is it 30? It's not 30. But close. Close to 30. And it still works. It's incredibly robust. They're incredible instruments. If anyone's getting rid of AC9s because they think like, oh, they're old and they're not supported, just grab it because you can fix it. Okay. So where am I here? Okay. So it has a tube cuvette. And on the side where you're measuring absorption, you've got a beam of light entering into this path length, which can be 5 or 25 centimeters long. And then there's a diffuser on this side. Why would we put a diffuser on this side? Yeah, to collect the scattered light. So you can get all that light that's coming at some funny angle into the detector. Okay. On the beam attenuation side, where we haven't talked about it, but you don't want to collect the scattered light because you want to measure the transmission of light that has passed through here without being absorbed or scattered. They have a very narrow detector, right? And Amanda's going to spend a lot of time talking about the detectors and optimizing that for beam attenuation. And so by difference, this measurement minus this measurement, of course, we get the scattering spectrum, which is great. Okay. The problem is that some of the scattered light is not collected by the absorption tube, right? So if some of the light scatters out of that tube, we call it absorption. The other problem is that some of the scattered light is collected by the attenuation tube, so we're underestimating attenuation. And that's just the finite limits of detection. And so you need to do some reporting on what your AC9 looks like, or ACS, or any absorption meter looks like. Okay. So you're so excited you get your ACS from the factory. You are ready to go out and jump on a boat and start making some measurements. What's the first thing you're going to do? Calibrate it. Gold star, yes. Calibrate it in the lab. Because you don't know what happened to it while it was being shipped, right? So do a water calibration, do a bunch of other things, but calibrate it in the lab. Then you're going to put it on a frame or a vehicle or a profiler or a mooring, or you're going to drag it behind the boat. I don't know what you're going to do, but you got to set it up. All of your tubing has to be black. Why would you want black tubing sucking water into your spectrophotometer? Why don't you want to just use a night break tubing so you can see the flow? It's going to let light in, and it's an instrument that's measuring light. So you want to actually, I think having a little, if you don't have these dongles on here, sometimes I bring mine together so that you're not piping light into the instrument. If you're putting it on a mooring, you can use copper tubing, which will cut down on biofouling. Literally the plumber's tubing. There's an air valve up here at the top, which as the water is drawn in, allows the bubbles to escape, because bubbles are not your friend. I tend to seat mine in the bottom. I have a little cup for it that it sits in, and then I bracket the top. You don't want to bracket the top on the bottom because you can tweak it and then change the alignment, and the alignment of the instrument is really important. And then what are you going to do? Calibrate it. Because you don't know what you've done once you've configured it. So you always want to calibrate it. Basically, you're just going to calibrate. Anytime you look at your instrument, just calibrate it, right? Just every time. Okay. Calibrate it on the frame.
Remember, it's a spectrophotometer. In your lab, your spectrophotometer, you calibrate every time you take measurement. And for some reason, people think that they see something different. They don't recalibrate.
Because it's not in the manual. Right? It's not in the manual. It doesn't say calibrate every time you look at your instrument. It should. But you also wouldn't put your spectrophotometer on a frame, right? You're like, don't touch it. Don't lean on it. Just people are throwing these things around. Okay, and then you deploy it. Take it down to depth. You're going to purge out all the bubbles. You're going to take out that upcast and then start your cast. And Amanda will talk a lot when you guys do process the data from the cruise about why you don't want to why you want to select, just the downcast. Okay, so then we're going to calibrate it. When we get back, we've gone on this great experiment. You want to come back and you want to calibrate, or you want to calibrate every day on a cruise. Just calibrate as much as you can, just to keep track of everything, if you have sources of clean water. Okay, so here's some old data from an AC9 that Emmanuel and I published a while ago. And this was, I can't remember where we were, actually. Somewhere, maybe in Friday Harbor, Orcas Island, I don't know. Anyway, we have this really nice profile of absorption at 9 wavelengths. Got some weird thing going on here, but otherwise it looks really nice. And you don't know how often you see these kinds of profiles, and you're like, wow, great data. And then you notice that the person publishing it never published the spectrum. Because if you publish the spectrum, you got that, which looks weird. First of all, it's only 9 wavelengths, and we're used to hyperspectral. But I do the 9 wavelengths just because I think it's very illustrative. What is going on here? So this is this upper layer. This is this lower layer. We've got this garbagey thing here. What do we need to do? Yeah, calibrate and subtract your water calibration, right? Look at your calibration. What's it look like? Look at the factory one. So when we did that, of course, we get like beautiful spectra, right? It's beautiful, gorgeous. All right, so we subtracted the water. Okay. Then, and here's an ACS example. So here are some pure water scans, bunches of them. For this particular one, everything was really negative. Our pure water cals were really negative. What did that tell us? Well, so when they, in a nice way of saying it, when they provide you with the instrument, they're subtracting their factory calibration, right? And so you should get 0 when you do a pure water cal. If you don't, and yours is negative, your water is cleaner. Something to think about, okay? So, but the point is you should do it. You should do your calibrations. And Mike Tradarcy published a paper a couple years ago where he looked at how at one of the wavelengths, he looked at the change in the pure water cal over time, and he found that over 200 days, there's actually a drift. So you should know your instrument. Every instrument is different. Mine all behave differently. They're like pets. They all need different things. So, but just the point is you can't just trust these calibrations or the calibration you did 200 days ago. Sensor uncertainty. Okay. So figure out your sensor. Know your sensor. It's a relationship. Okay. Then we talked about temperature and salinity of your calibration water versus the temperature and salinity of your sample. Right? So if your sensor is calibrated at 25 degrees and you work in the Arctic, the pure water cal at 25 degrees is not really going to apply. So you have to do corrections. Okay? Oh, and that's exactly what I said. Okay. All right. So this is natural variability, that there's a natural variation in your water compared to your calibration. So you have to account for that natural variability. All right. So here's an example. Again, AC9, so nice and blocky. This is the beam attenuation. This is the absorption. Ooh, it's negative down here. When you do the temperature and salinity correction, sometimes you find that things begin to look more normal. And we'll see that the reason why this is really, really critical is because of the null correction. We are back to the null correction. All right, so here's the ACS. There's the correction for pure water. Fantastically different. You do notice that because we had a big negative calibration, now our value is much higher. Gotcha. So by a lot, 0.5, so pure water correction is really important. You have to also correct these for scattering. So here's an absorption spectrum. We've got a big signal here. I erased it. What are we going to do with that? There's scattering, loss in the ACS. How do you all correct yours? Someone be brave. Tell me what you do. Everybody raised their hand when I asked if you worked with ACSs and AC9s. How many people raised your hand? Now you have to raise your hand again. It wasn't just the people in the back, and it wasn't just you. No one else has ever worked with an ACS or an AC9? No. I saw hands raised.
Yeah, I did it, but I didn't correct for skipping.
Right, but did you measure how many people how many collected a scan? Any sort of data. It's okay. Got one brave soul. Okay, that's okay. That's why you're here. I know, gold star. No, seriously, I mean, this is the whole point. You know, have you done the calibration? Have you done the water correction? Have you done the scattering correction? All of these things are really critical steps, but most people don't do them. And you can be off by a lot. Look what you get. You get it. Oh. Yay!
I don't have many of those, just did the great
Okay.
ones.
So again, we need to do these corrections. All right. So there's a bunch of different ways, and Emmanuel's going to talk about a bunch of different ways. The first one is just subtract that offset all the way along, right? The assumption is that the scattering is spectrally flat, right? That scattering is equal across wavelengths. And we will find out whether that is a really good assumption later in the week. Okay? It's the same thing we do here. We did in a spectrophotometer. Okay, the other one is to subtract to actually calculate the scattering spectrum and then subtract that, because with this instrument, unlike with the integrating sphere, if you have a measurement of C and you have some initial measurement of A and you subtract them, you get B. And so now you have a shape of B, and this is not spectrally flat. But you can say, well, if all of that's due to scattering, I'm going to apply that value to this shape, and I'm going to get a spec that actually is spectrally varying like this. And I can use that for my correction. That makes a lot of sense to me. Okay? So you're correcting some function of B. Okay, some fraction of B. Okay, whoa. All right. The other is to, wait. Is that the one? Yes, okay. So this one, oh, it's the same thing, but for the scattering spectrum. Now, are you going to do which other correction are you doing? Are you doing the back scattering correction?
No, we don't know, because we're not measuring so some people have suggested we can measure correction.
Mm-hmm.
But we're going to use another one by what, because it's just.
Oh, the records, yeah. So he says that signal in the infrared, maybe it's just there's a part of it that is scattering and a part of it that is absorption, which I agree with. How much? 14%, 70%? It sort of depends. But you guys will do that correction. You can compare. And you can figure out, and that's your uncertainty. Right? Okay. All right. So that's what you're going to do. All these steps. And that's it. Oh, no. One last thing. God, that's a long day. Sorry. Oh, just talk about absorption measurement, Collin, and do it in an hour and a half. Okay. If I'm exhausted, you guys are really exhausted. So one of the beauties of doing the filter pad measurement is that you can separate particulate and dissolved, right? And that's great. But you do it on discrete samples. So about 10 years ago, Emmanuel and Wayne Slade came up with this really clever way of doing the same thing with an AC9 or an ACS. Actually, it was an ACS. And so what they did is they put it in an inline system on a ship, and as the water flowed in, they did the automated filtering so that you could collect whole water and then filtered water and then whole water and filtered water. And you could do that every 10 minutes or 10 minutes on the hour or whatever schedule that you wanted. Now, there's a huge beauty in that. Because when you have instruments on a ship, you know, they get dirty, water gets dirty, tubing gets dirty. Don't talk to me about dirty tubing. But the beauty is that the dirty tubing shows up in both readings. and the drifting instrument shows up in both readings. And so if you had some crazy absorption, total absorption measurement, or unfiltered, and you had some crazy dissolved measurement, so unfiltered and filtered, and then you subtracted them, because all of the garbage, if I was a perfect, artist, all of the garbage gets subtracted out. And so it yields a particulate absorption that's independent of any sort of calibration or drift. And so this is exactly what they did. So here's the first generation of this setup. This is absorption as a function of time at one wavelength. There's the total, filter turns on. Back to total, filter turns on. So you can actually extrapolate and get a continuous measurement of filtered and a continuous measurement of total. And then you can subtract them. And you end up with your particulate absorption, which is on the order of a very, very small number. This was from the equatorial Pacific. And here is a spectrum associated with that time series. And I will just say, like, crazy low values. The resolution on the instrument from the factory is 0.005. That's the best they can get you in terms of absorption per meter.
Uncertainty, not the resolution.
I'm sorry, the uncertainty. The uncertainty. Thank you. So they say that they can resolve you to here. And now we have basically an absorption peak here on the order of less than half of that uncertainty. So it's a really incredible approach. And you guys are going to do it in lab today and tomorrow.
And
So.
we hope to set up an inline system like this
On the cruise in 3 weeks. So you'll get a perfect opportunity to see how this works.
But you can do it, and we've done it even before this, you can do it when you go on a cruise.
Mhm.
You can do one drop total, bring the instrument to the surface with the equator lake, which is an incredibly clear environment, one drop with a filter. And as long as the water is not changing between your filter and your total, you can apply this method. You did it diving with a filter that I did one night dive in the spectrum down on my back, then I took the filter and retraced my steps again to do this.
Just warning,
So-
it has to be same water.
You're assuming that dissolved materials have not changed between the
Mhm.
measurement, or you interpolate between them and assume that the linear interpolation between them is the right approach. But you can monitor that with a sit-on fluorometer in line too, so you can see.
So you know there's no changes.
When you cross the front,
Yeah.
as you will go.
Yeah. So you should always keep track of what this looks like.
But this brings us to another quite
Can-
control issue.
Okay, can I just say one thing before you get to that? Because I just want to, you can also put more filters in line. Because you asked questions about size fractionation. So I put a 5 micron and a 25 micron, or 20 micron filter in there. And so then I get total 20 microns, 5 microns, 0.2. And so you can end up with size fraction intervals of absorption continuously. So,
So just one thing that I tell, I think that everybody coming from this class should remember to do. So we talk calibration. There's something else you want to do every day with your AC meter. Once a day, you measure dissolved on all your AC meters. I don't care if you use it, you use two, one for total, one for dissolved. Once a day, the one you use total, put a filter on. Why? Why would you once a day measure dissolved on every one of your AC meters? But how would you see it in the dissolve? How do you expect the dissolve spectrum to look like? Exponential, and if it does not look like one with the calibration you apply, this calibration might not be the one you want to use. You see, calibration is not trivial. It's time, you get variability, and as you go on a cruise, you can post one,
other really nice thing about it is because you do expect an exponential. When you don't get it, if that's what you expect, right, you fit your curve. What do you know about this in the infrared region? What's happening in the infrared? Why is your measured value much lower? We haven't done any corrections yet. Temperature, right? The temperature and salinity shows up here. So what if you didn't have a CTD with you to do your temperature correction? You can actually use that as an estimate of temperature. So you can do the back calculation and calculate temperature from your dissolved absorption reading, which means that you just got 2 instruments for the price of 1. And if you plot this as a function of depth, this delta absorption, you'll find a really nice profile of a mixed layer and a gradient, and then your deep mixed layer. You'll get your temperature profile back.
You can use these to know what the delay is in the water going through your instrument versus the CTD. Because now you put the temperature from the CTD, and the delay in time of seeing the front of the mixed layer tells you when the water got to your sensor after it went through the CTD. You really the CTD. 40%.
Yeah, so then you can, if you calculate this, then you can apply that to your unfiltered AC9 temperature correction, just to check. Done. Done. I'm not even looking to see if there's another slide because I don't want to see it. And now you can't see it. I was done. That was my last slide. Good. I did everything. Okay. All right. Am I done for a couple of days now? I'm done for a couple of days. Am I done? Yes. Well, except for lab.
Yeah, we have 15 minutes until lunch.
Hmm?
Nice job.
I'll drop it